Hello everybody, let us talk about quantum entropy. Before we get into quantum entropy, let's see what classical entropy is, and classical entropy is also known as Shannon's entropy. Classical Shannon entropy measures the uncertainty in a probability distribution. So let's say if pi represents the probability distribution, this relationship of hx equal to minus sigma I pi log pi, this relationship is basically for the entropy of the classical system, and it represents the average information present per message in the communication theory. Analogous to classical entropy, we have quantum entropy. In quantum mechanics, states are not just probability distributions but density operators. So we represent the states of the quantum systems using density operators, and we also know that the density operators can be both pure, can represent both pure and mixed states. Now, for a quantum system described by a density operator, we also know the characteristics of the density operator, that it has to be positive semi-definite with unit trace on a Hilbert space H. So these are the characteristics of the density operator. So for a quantum state described by a density operator, the von Neumann entropy is defined as, so this is how we write the von Neumann's entropy, basically the quantum entropy. This is S of rho, where rho is the state of the quantum system and rho is the density operator, and this is given by minus trace of rho log rho. This is the quantum analog of Shannon's entropy for probability distributions. Now, why this definition is there? So let us give a deep dive into the definition of this von Neumann entropy. Now, a density operator rho, which is basically a matrix, generalizes a probability distribution. Why it generalizes? Because density operator can be used to represent the system both for pure and mixed states. Whereas if you remember, the state vectors can only represent the pure states. So therefore a generalization was thought of in terms of the density operator, which can represent the quantum state for both pure and mixed states. So therefore we say that a density operator rho generalizes a probability distribution. Now if we diagonalize this operator, then we will obtain, I will show you how to diagonalize it, but after we diagonalize this matrix rho, we can derive rho equal to sigma lambda I and the outer product of psi I. That means this relationship is in terms of the eigenvalues. So we'll see how to diagonalize, where set of lambda i's are the eigenvalues, all eigenvalues are greater than or equal to 0, and the sum will be equal to 1. And this set of states which are represented by ket psi i's are orthonormal eigenstates. So thus in the eigenbasis of rho means when we are representing rho in terms of the eigenvalues, so that will be called as the eigenbasis of rho. The entropy reduces to, so this is the entropy value, von Neumann entropy will be reduced to this formula, which is exactly, so this formula is almost exactly of the shape of the Shannon's entropy, but in terms of the eigenvalue distribution rather than the probability distribution. So let us look into the proof of this. When I say that rho needs to be diagonalized, let's see how the diagonalization of the rho will take place. So in the proof, the first step is the diagonalization. So any Hermitian operator, we know that rho is a Hermitian operator. What is a Hermitian operator? The adjoint of the operator is equal to the operator itself. Now any Hermitian operator can be diagonalized. So that means we can express the operator as u d u adjoint, where u as a decomposition with u and a diagonal matrix, where U is a unitary matrix and D is a diagonal matrix, and the diagonal elements are basically the eigenvalues, and where U dagger represents the adjoint of this unitary matrix U. Right, so this is how we decompose or we diagonalize the Hermitian matrix rho, which is the density operator, and by applying this decomposition, we will diagonalize. That means in the diagonal, all the eigenvalues will rest. The next step in the process is the logarithm of the operator. So we define the logarithm of rho in the spectral sense. So let us take the log on both sides. When we take log on both sides, so this will give us log of rho equal to, so u and u adjoint will not depend on the logarithm. So u log d, u adjoint, u dagger. So therefore, whereas we know that what is this D matrix? D matrix is the consists of all the diagonal elements, and the diagonal elements are the eigenvalues. So therefore, when we take the log value, so log D will be equal to the diagonal of log lambda 1, all the we will have to take the log of all the eigenvalues. Now the third step is the time invariance, the trace invariance. The trace is unitarily invariant. So what do I mean by this? So trace of an operator A will be equal to trace of this decomposition with u dagger AU. So when we used to calculate when we used to calculate trace, the trace will be equal in both the cases. That's why we say that the trace is invariant, unitarily invariant. Right. So what is unitarity? Unitarity basically tells us that u dagger into u will be equal to the identity matrix. So that u dagger and u represents the unitarity, and now we say that trace is invariant to the unitarity. So that's how this relationship defines the invariance of the trace against unitary property. So let us, in our case, the A operator is rho log rho, right? So we will have to take the trace of rho log rho, and this will be given by, because we actually are interested in calculating the trace of this, because this is how we defined the von Neumann entropy. So this is equal to, you substitute the value of rho as u d u dagger, and log rho, we know this is equal to u into log d u dagger. So this is, we are replacing rho and log rho with the specific values. Rho will be having u d u dagger, and log rho will be equal to this. So you will see that here u and u dagger will lead to identity, u and u dagger will again lead to identity, and what we are left with is trace of d log d. Right. So the fourth step is simplify the trace. So if you simplify the trace, so in that case, since d and log d are diagonal matrices, so replacing the diagonal matrix with the eigenvalues, this will be equal to, the trace will be equal to the sum of the diagonal elements basically. So that will lead to this expression, and this expression is basically the von Neumann entropy. So therefore we started with the von Neumann entropy of the original definition, which says that the von Neumann entropy or the quantum entropy is given by minus of trace of rho log rho, and we have expressed this expression in terms of the eigenvalues. So S rho is equal to sigma I minus sigma I lambda I log lambda I. Now there are certain important properties of this relationship, which says that number one is purity. Now if rho is pure, that means if the density operator is pure, that means density operator will be an outer product of psi, then eigenvalues are, because then the eigenvalues will be given by 1 0 0. There will be only one eigenvalue for the pure case, and this eigenvalue will be equal to 1. Then eigenvalues are 1 0 0 0. So if you substitute these eigenvalues into the von Neumann entropy formula, which is equal to eigenvalues into log of eigenvalues, then if you substitute this set of eigenvalues into the von Neumann entropy relationship, you will find that the von Neumann entropy is equal to 0 for a pure state. So therefore we can say that a pure state has 0 entropy. Now let us look into another very important concept, which is known as maximally mixed state. For d-dimensional Hilbert space, the maximally mixed state is defined as, so this is how we define the maximally mixed state, in which the density operator is equal to 1 over d into the identity matrix. Identity matrix is of the dimensions of d cross d. ID is d cross d identity matrix. Since the identity matrix has all eigenvalues equal to 1, so this is an important point to note down, that the identity matrix will have all its eigenvalues equal to 1. Multiplying by 1 by d, right, will give me the eigenvalues to be 1 over d, because in the density operator we have 1 over d into id. Id has got the eigenvalues as 1. So 1 multiplied by 1 by d will give me the eigenvalues, and all eigenvalues will be equal to 1 by d, right. So using this value of the using this eigenvalue, which is 1 over d, and if you use this von Neumann entropy formula, we will get von Neumann entropy equal to log d. So in the case of maximally mixed state, the von Neumann entropy will be equal to log of d, where d is the dimension of the density operator, right. Dimension of the Hilbert space. Anyhow you can define d in terms of identity matrix. D is the dimensions of the Hilbert space also. So d you can relate it with the dimensions of the density operator and so on. So therefore important point is that the von Neumann entropy for a maximally mixed state is log d. So let us try to interpret this relationship, that von Neumann entropy is log d for maximally mixed state. Now this is the maximum entropy possible for a d-dimensional quantum system. So for a d-dimensional quantum system, this is the maximum entropy possible. What is the maximum entropy? Log of d. It corresponds to a state of complete uncertainty. So this is the maximum entropy possible. So therefore it is we can say that this is complete uncertainty which is possible for the maximally mixed state. This value of von Neumann entropy to be equal to log of d. Now let us look at certain special cases. When d is equal to 2, then the von Neumann entropy is 1 bit. Basically it is maximally mixed qubit, right. When d is equal to 4, you have 2 qubits of this is equal to 2 bits, right. And when d is equal to n, what I mean to say is that entropy, as n increases, entropy grows as log of d. So this is an important point for the maximally mixed state. So we have discussed about the entropy of the maximally mixed state, then the entropy of the pure state, and in general we have tried to establish a relationship between the von Neumann entropy and the eigenvalue in terms of eigenvalues. And at the start we defined the von Neumann entropy as minus trace rho log rho, and we have also understood that this von Neumann entropy formula is very analogous to the Shannon entropy in the classical world. Thank you.